Hi, everybody. Today's topic is special right triangles. Today is March 25th. The idea behind this topic is to not have to show any work, which most of you will like, but the topic can be a little challenging at first until you get used to it. This is the note packet that you'll need to go through the lesson with me. We've been working with right triangles since we started our trigonometry unit. If it's classified as a special right triangle, there are some circumstances about the measures of the angles or the measure of the sides that will allow you to do calculations really quickly. You can really do some mental math with this. So we're going to start with the easiest special right triangle. It's based on what we see in a square. So if you start with a square and you draw one diagonal in, you're going to form two triangles. Now, there's my square. Some of the properties that we know from the square are 4 congruent sides, 4 right angles. We also know that when the diagonals are drawn in, they're both congruent to each other. They bisect each other, forming 4 equal pieces. So when I draw that diagonal in, let's focus on a right triangle that's created. The diagonal does bisect your 90-degree angles, so the angles with the blue arc marks are both 45 degrees. So this is called a 45, 45, 90 right triangle. If you look at the angles, the continued ratio of 45 to 45 to 90, that continued ratio reduces to 1 to 1 to 2. So a 45, 45, 90 always has this property, and it also is something that you can apply to the sides. So what is the relationship between the sides when the angles are in a ratio of 1 to 1 to 2? We can pick any side length we want for our isosceles right. So for the first example, I'm just going to say that the two congruent sides are 5. What I want to do, though, is find the length of the hypotenuse to see how it relates to the other two equal sides. So I'm going to use the Pythagorean theorem to find my missing side. If you were inclined, you could use trig of 45 degrees on the sides to see if you could find the hypotenuse, but I think that the Pythagorean theorem is the easiest. So I'm going to go ahead with my calculations, and I'm going to go ahead and square root. 50 is not a perfect square, so I will have a square root radical in my answer of 5 radical 2. Well, this first example really doesn't show me what the relationship is, so let's go ahead and do another trial. In trial 2, let's just say the sides are both 7. I'm going to go ahead and use the Pythagorean theorem to find my hypotenuse. So at this point, I can see c squared is equal to 98. That is not a perfect square. So I'm going to have to get a square root radical. And what I can see is the hypotenuse is 7 radical 2. I don't know if you're seeing a pattern yet, but when the sides were 5, think about what the hypotenuse was. When the sides are 7, think about what the hypotenuse is. And then let's try a third one. This time the sides are 100. Can you predict what the hypotenuse will be? As I go through the Pythagorean theorem, c squared is 20,000, and again, that is not a perfect square. And when I simplify that, my hypotenuse is 100 radical 2. So hopefully you're seeing the pattern. The sides are going to be equal, and then the hypotenuse is really the same as the side lengths times radical 2. We do have an official theorem for this 45, 45, 90 right triangle. If you know the length of any of the sides of your isosceles right triangle, then the length of the hypotenuse is just times radical 2. In the example or the picture, you can see the sides are 1. Technically, for the hypotenuse, there is a coefficient of 1, radical 2. So this is following the pattern of the last 3 trials that we just saw. So if they give you the hypotenuse, I'm sorry, if you have to find the hypotenuse, it's going to be leg times radical 2. But you also have to keep in mind that sometimes they will give you the hypotenuse and you have to work backward to find a leg. So it would be the inverse function. We would do the hypotenuse divided by radical 2. So this is the opposite function if you have to find a missing leg. So let's try some. For example, number 1, I can clearly see this is a 45, 45, 90 right triangle. One of the legs is 8. Remember, you can pause the video at any time if you want to try the examples before I reveal the answer. But I know that the hypotenuse should just be 8 radical 2. And there it is. For number 2, they're giving me a leg. They did not provide the third angle, but I do know that it's 45 degrees, which means X should also have a same leg length of 14. And then if both legs are 14, my hypotenuse should be 14 radical 2. So there's no math required. It's just straightforward knowledge. Number 3 is a little more challenging. They did not provide a leg, so we're going to have to work backward. So since they gave me the hypotenuse, we're going to divide by radical 2 to find the leg. We're working backwards, and this is what it looks like over here on the far right side. 8 divided by radical 2. Right now, this is not math that I could do in my head, so I'm actually going to show the work on this. Since I'm not allowed to have a radical in the denominator, I'm going to rationalize. We're multiplying the entire thing by radical 2 over radical 2. This is just a manipulation of 1. And when I multiply in the numerator, I'll have 8 radical 2. In the denominator, I'll get radical 4, which is the whole number 2. And then I'm going to simplify, and my missing leg is 4 radical 2. There is a pattern here. We'll see if you can figure it out by the time we get to the next problem. So in number 4, we're working with the same type of idea. They've provided the hypotenuse, but they have not provided the length of the leg. I can see, though, that they're giving me a square. I'm not assuming anything, that if this is a square, the diagonal does bisect, and these are both 45-degree angles. So again, I'm going to start with 10, and I'm going to divide by radical 2. And I'm not allowed to have radical 2 in the denominator, so I'm going to rationalize. In the numerator, I'll have 10 radical 2. In the denominator, it's radical 4, which turns out to be the whole number 2. And then I'm going to simplify, and the answer is 5 radical 2. So if you think about example 3, the hypotenuse was 8. I ended up with 4 radical 2. In example 4, the hypotenuse was 10, and my leg was 5 radical 2. So if you can remember the trick, when you're working with two angles that are the same, we're using radical 2. If you're working from hypotenuse backward to leg, you're going to cut the hypotenuse in half and then multiply by radical 2. And that trick does work every single time. The next type of special right triangle is called a 30, 60, 90 right triangle. If you reduce the ratio of 30 to 60 to 90, the angles are in a continued ratio of 1 to 2 to 3. And because that ratio exists, there is some special characteristic about the side lengths that will also exist. Here's a diagram showing you 30, 60, 90. We know from a previous lesson that when you identify the largest angle, you'll find across from it the largest side. Same thing with the smallest angle. Across from that is the shortest side. So the side across from 30 degrees is always classified as the short leg, and then 60 degrees across from that is the longer leg. The hypotenuse will continue to be the longest side. It's always found opposite the 90-degree angle. So if you can identify who's the shortest side and the hypotenuse, we'll be able to do some quick mental math. So is there a relationship? We're going to go through one example, and then we'll see where it takes us. I randomly chose the shortest side to be 4, and I want to know what's the relationship between the short leg and the longer leg. So I've placed an X there, and I'm going to calculate the longer leg. Based on what's present in the diagram, I'm going to have to use a trig ratio to find X. So if I'm here at 30, 4 is my opposite side, X is my adjacent side. Opposite over adjacent is tangent. So tangent of 30 equals 4 over X. If you'd like, you can make this a proportion by placing a 1 in the denominator under tangent of 30, and we will cross multiply. In this case, you're going to have to divide both sides by tangent of 30. Now, I did this on my iPad, and it gave me 4 radical 3. So, not sure if you're seeing anything happen there. Really maybe doesn't look like much yet. We still need to find our hypotenuse. So, I'm going to label that variable y. I'm going to continue to work with the 30-degree angle. You can work with the 60-degree angle if you like. Since I'm working with the 30, I'm going to use side 4, which is opposite, and then y is my hypotenuse. So for me, that will be the sine ratio. So sine of 30 equals 4 over y. Again, we're cross multiplying, and this is a case where we're working a little bit backwards. So you're going to divide 4 by sine of 30, and the iPad gave me 8. So this may not seem like much. If I write a continued ratio comparing the 4 sides from shortest to longest, I will have 4, 4 radical 3, and then 8. These all have a common factor of 4, so my reduced continued ratio is 1, 1 radical 3, and 2. All 30, 60, 90 right triangles have this relationship. You can see it in the diagram. 1 is my shortest side, my longer side is 1 radical 3, and my hypotenuse is 2. So we have a theorem that goes along with our 30, 60, 90 right triangle. The length of your hypotenuse will always be twice the length of the shortest side. So all I have to do is take 1 and multiply by 2 to get the hypotenuse. The longer leg across from your 60-degree angle is always going to be the short leg multiplied by radical 3. So we have 3 different angles in this case. We're using radical 3. If we have 2 of the same angles, like 45, 45, 90, we're using radical 2. So again, if you want to find the hypotenuse, it'll be the short leg times 2. If you want to find the longer of the 2 legs, it will be the shorter leg times radical 3. And keep in mind, they don't always provide us either of these 2 sides. They could be providing us the longer leg, which means we would have to work backward. So in our first example, number 5, even though they didn't fill in the third angle, I do know it's 30 degrees. So 8 is my short leg. From the short leg, it's easier to find the hypotenuse. So I'm going to multiply by 2. And then to find the longer leg, x, I'm multiplying 8 by radical 3. So if I know this quick trick, mental math, x is 8 radical 3 and y is just simply 16. Let's try it in example number 6. This time though, they did not provide the measure of the shortest side. They gave me the longer leg. So in a case like this, we have to work backward. I'm going to start by taking my longer leg, 12, and I have to divide by radical 3. Just like some of the other examples, we're not allowed to have a radical in the denominator, so I'm rationalizing. So the numerator will be 12 radical 3. The denominator is radical 9, which simplifies to a nice whole integer, and then I can reduce it, 4 radical 3. Once you know the short side, all I have to do is multiply by 2 to obtain the hypotenuse. You're multiplying the coefficient 4 by 2, not the radical. They're different types of numbers. We don't mix our apples and our aliens. We need to only multiply by the coefficient. In example number 7, there's my largest angle. The unmarked angle is my smallest angle, but what they're providing me is 6, the hypotenuse. I can work backward to obtain the short side simply by dividing by 2, which means x will be 3. And then once I know the short side, I can find y simply by multiplying by radical 3. So we have 3 and then 3 radical 3. And in number 8, they have the triangle facing a different way, so make sure you orient yourself, finding the smallest angle, the largest angle. Based on what I see, though, 16 is my hypotenuse, so again, just like example 7, I'm going to work backward. I'm going to first obtain x, which is my short leg, so it will be half. X is 8. And then once I know that, I'm going to simply multiply 8 times radical 3 to find my longer leg. So remember, this might seem a little bit confusing at first. If you don't care for this technique, you can always go back to using trig and Pythagorean theorem, or a combination of 2 trig functions. But if you like this idea, and I do want you to practice this on tonight's homework, hopefully this will just give you some mental math and it will make some calculations a lot easier. This is homework number 103 in your packet. It's labeled as special right triangles. My suggestion is maybe go through and do all the 45, 45, 90s first and get used to that idea, and then maybe go back and do all the 30, 60, 90s. For many of these, you are going to have funky, weird fractions with radicals, so just know that that is possible. As always, if you're going through homework and you get stuck, please feel free to email me. I'm checking my email every single day, and I'm keeping it open all day. You can text me, or you can call me at home. So until I hear from you, have a great day.